Before we get started, I just wanted to give a few quick kind of updates on kind of what's new at ACCRE. So one of the things we're really excited about and is a new software tool that we've been kind of trying to tell more users about is this tool called Singularity. So if you've heard of Docker, who's heard of Docker in here? Anyone use Docker? Okay, cool. So Docker is a tool that essentially allows you to run containers within an environment. So if you're familiar with a virtual machine, you can think of it sort of as like a lightweight virtual machine. Singularity, on the other hand, is you can think of it like Docker, except it's safe for a high-performance computing shared environment. So Docker, due to security concerns, essentially gives you root access from within the scope of the container, which, believe it or not, we don't want our users to have root access on the cluster. So Singularity sort of gets around that, and it allows you to either convert like a Docker image to a Singularity image. And the way it works is within the container, you essentially have the same permissions that you would have outside of the container. So in that way, you're able to sort of run your analysis within a more consistent platform. So the big, one of the big pushes in the scientific computing community recently has been reproducibility. So if you can run things from within a container in sort of a platform agnostic way, that really enhances reproducibility. And it also, in our case, is important when it comes to installing software. Some software packages have very, very specific requirements and dependencies that they need. Unfortunately, we can't keep everyone happy with all the software and libraries that are available in the massive shared environment. But if you could run things from within a container, you effectively have control of what's installed, even if it's like in a shared, a typical system directory like user local or something like that. So just to give you an extremely quick demo of how this would work, I've created an Ubuntu 16 image, Singularity image, that I can run on the cluster. So can everyone see this? Maybe make it a little bigger. Okay. So right now I'm just logged into one of our gateways. And we currently are on CentOS version 6.8, all right, which is a pretty old operating system. I think CentOS 6 came out like 4 or 5 years ago, maybe. So we're actually hoping to upgrade, or we were planning to upgrade the operating system later this year, and we'll be announcing that probably in the next few weeks. But in the meantime, if you have more recent library requirements that you want, one option is to use Singularity. So it's available via set packages, and once you have your image, it's as easy as Singularity shell image name. And now the operating system is Ubuntu 16.10. So a completely different Linux distribution that I'm sort of running within. I have access to all of my home storage, so I can still see all my files. I can still see my Scratch directory. So all of your ACCRE storage is available from within the container. In this case, I've actually installed a version of Python, kind of an up-to-date version of Python 2.7 within the container as well. So anywho, if folks are interested in using containers and you could see some benefits to this, we're kind of in the process of developing documentation that we'll put up on our website, and we'll advertise it a little bit. But if in the meantime folks are interested, I would encourage you just to open a help desk ticket, and you could even come over to ACCRE, schedule an appointment, and we could walk you through the process of creating your own custom image.
Do you have a set of images that are generally available?
So that's kind of on our radar. That's on our roadmap. So right now, not really. But what we would like to do is have a stock Ubuntu 16 image that allows you to mount all of your ACCRE storage, CentOS 7, CentOS 6, Ubuntu 14, and if there are other other platforms that folks are interested in, we could consider those as well. So with that, I we'll stop talking about containers and hand it off to our speaker, So Chris Fonnesbeck is an assistant professor in VUMC in the Department of Biostatistics. He is also the creator of PyMC, which is a widely used Python package for like Bayesian statistics. I think we'll talk about it a little bit today. And he is also, what is your title? Benevolent Dictator for Life of PyMC, which I didn't know was a thing, but I Googled it and it's actually a thing. So yeah, he's going to walk us through kind of some of the popular data analysis tools that can be used within Python on the cluster.
Thanks. All right. Oh, pre-applause. I've never had pre-applause before. All right. Thanks, everybody, for your interest in showing up. Today's just going to be a little tour of using Python for data analysis. So I'm not going to show you how to use Python. A lot of you have used it before. I know that because there are some of my former students in here. But more specifically, I want to show you how it might be applied to doing data analysis. Because Python's used for a lot of things, right? It's a very general purpose, high-level programming language. So sysadmins use it, and web developers use it, and so do some data analysts like myself. And so the only intro to Python I'm going to show you, for those of you who had never seen it before, let me just hide some Jupyter stuff here. That's what Python code looks like. Has anybody never used Python in here before? Anyone? Okay, yeah, there we go. One in the corner. Okay, so what throws new users off is there are no braces or brackets enclosing code blocks. It's all done via whitespace, which initially strikes people as completely insane. But it actually works out really well, and it forces you to be very tidy with your code. We've got some data here in a data structure called a list, and this is a function you would never actually have to write because this code becomes available to you already in Python, so it's just for illustration. Functions specified with this def statement, name of the function, and then the arguments of the function. So it takes some data and it calculates a mean. This is just a variable initialized to a floating point value, and it's, again, high-level interpreted language, so you don't have to declare types or anything like that. And then a loop, adding each value of x to the sum, so it's got an increment operator there, and then we're just returning the sum divided by n, the length of the data, and it gives you the mean. Okay, so that's Python code. So just kind of a justification for its existence here as a Python, or as a data analysis platform. There are a lot of good reasons to use Python. That syntax that I just showed you is extremely easy, not only to write, but also to read. So I collaborate with clinicians, doctors, psychologists, biologists, and they can't read C code by and large, right? But I can pass them some Python code and they'll be able to follow it if it's annotated well enough. But it's also very powerful. It's not unusably slow. You can do a lot of things with it. It's extremely flexible. It's interactive, so I'm going to show you an interactive session of Python right here in this notebook. So what we're using here is what's called a Jupyter notebook. It's just an interactive shell that runs in a web browser. So you can write scripts, you can write applications, but then you can also run it interactively like you would R or MATLAB or something like that. Very important thing is it's extensible. So again, as a general purpose programming language, it does come with a lot of what we call batteries included features, a lot of things that you don't need third-party packages for, but the real power comes in with all the amazing stuff that third-party developers have contributed that have made it a great scientific programming platform. And that's really what I'm going to cover today are some of the third-party libraries that you can use. And then, of course, the whole free and open thing, right? It's open source, and so you don't have to. We've just had our SAS licenses upped in the medical center because I don't know if you're aware of this, but VU Medical Center separated. We did a Brexit, we did a Vexit, and we're no longer an educational institution, believe it or not. And so we don't get SAS educational discounts now. So our licenses are now $14,000 a year for the pleasure of using SAS. so I don't. And so, so there's a whole bunch of really good science. I'm going to cover a bunch of these guys here. This is really what sells Python to you as a scientist for doing scientific programming. We'll cover some of these guys: NumPy, SciPy, Matplotlib for plotting, Pandas, and more. And I'll step you through some of these here. So, NumPy really gave Python its legs as a scientific programming language. What it gave Python was the ability to work with arrays, do linear algebra. So it leverages C libraries, BLAS and LAPACK, allows you to do linear algebra operations, which are very important. Again, for those of you unfamiliar with Python, we're just importing the NumPy library into our current session. And then we're lazy, so we like shorter aliases. Not that NumPy is particularly long, but conventionally we call it NP. So now I can access all of its functions by NP dot. So in this case, I want a range of values, of 10 values. I just do NP A range 10. The other thing you'll notice is that it's zero index, so we start counting it at 0, as all good programming languages do. So we end with 9 rather than 10. Okay. And one of the nice things that NumPy allows us to do is that if we want to perform operations on the elements of that array, we don't have to write logic to do that. So we can it vectorizes operations. So let me scroll this to the top so people in the back can see it. So what I'd otherwise have to do if I was writing this in C, right, is I'd create a loop and I'd add 3 to every element and I'd square that for every element. Well, here all I did was add 3 to x. So I added an integer to an array. Again, nice high-level syntax here. And there is a loop going on, right? But you don't want to do that looping in Python because Python's interpreted, right? There's a virtual machine running, and it's got to compile things to bytecode and then do all this other stuff. What NumPy is really a C library. It's a big C library, highly optimized, and there's an interface into Python, right? And so the looping's happening. It's just happening in C where you want it to happen because it's fast. Okay. Other stuff that it gives you, things that statisticians like, random number generators, yay. So these are 4 by 10 matrix of standard normal random numbers. And it's got generators for different kinds of random numbers as well. And then I promised you matrix operations. Dot is the dot product. Matrix multiplication, so y dot x just does the matrix multiply of that, okay? So, so the next big tool is Pandas. Pandas is much newer than NumPy. Pandas gives you an even higher level set of data structures than NumPy does. And it's really good for working with tabular data with labels, and the sorts of data that you would see as a scientist. It was actually created by somebody who worked as a quant, a financial analyst, and so working with lots of time series data. And it's extremely fast. Again, most of it's implemented in C or Python, and it's fundamental for doing the same sorts of things in Python that you might do, say, in R. So we're going to import that as PD. Now, I could just take you through various libraries and demo features, but that's kind of a boring way to do this. So what I thought I'd do instead is take an example and analyze, find some real data, analyze it for you, show you kind of a worked example, particularly given that we've only got less than an hour. So what I did, I actually found a nice example on Lorena Barba's website, who's a really good Python programmer and professor at George Washington University. And I stole her example, but I'm extending it a little bit beyond what's done. There's a reference to her site on the at the bottom of this page. So this is some climate data. So these are called global surface temperature anomalies. Any climate scientists in here? Nobody? A couple of people at Vanderbilt that work in this stuff. But anyway, so this is just a URL to a CSV file. And it just contains a couple of columns, one of which represents time, the other represents a measurement. And these anomalies are simply the difference between some measured temperature and a baseline somewhere. And so positive values means it's warmer relative to the baseline, negative cooler. And they often work in this kind of relative measurement because then it makes it easier to compare, changes in Ottawa to changes in Miami, for example. You don't want to compare their absolute values. So first thing is, how do we get the data into Python? So you could go to this website in your browser, download it, import it back into your Python session. But Pandas is really great because it has a whole bunch of data import functions, convenience functions. And if you weren't around in the Python community, let's say 5 years ago, you won't understand the pain that this solves. Importing data even with things like NumPy is not terribly convenient. So there's a whole bunch of read functions in Pandas with a variety of commonly used formats, even Sass, so it makes the transition easier. And by the way, what I did up here, if you're not familiar, this is a Python idiom called a list comprehension. And it's basically a one-liner loop that returns a list. So you can see the square brackets, which represents a list. And it's taking the Pandas library, calls dir on it, which is the same as if you call dir in a Unix shell. It shows the contents of that package, essentially. And then F returns each item, it loops over them, but only if the name starts with read underscore. So I just wanted all the read functions. So list comprehensions are a really nice little idiom. So here, the one we're interested in is read CSV, because we've got a CSV file coming in. And the nice thing is that Pandas allows you to just stick that URL straight in there. So all that was is a string representing the URL. And it went and got it and read it and imported it and returns a nice tabular data structure as we promised. You'll notice that the original data up here also had 3 lines of metadata. Tells you what it is, what the units are, and what the base period was. So this is the relative date, I guess the relative temperature that it was referring to. And so I did skip rows equals 3. So it skips the first 3 and starts reading. Notice it automatically figured out what the header was, and we've got a column here of integers, sort of an index, which is really nice. What we have here is what's called a data frame. Those of you who used R are familiar with this terminology. It's, again, a tabular data structure that has a bunch of attributes, a bunch of high-level attributes. So it's got a shape, so there's just over 1,600 observations in 2 columns. And you can do things like, describe it. So it gives you some statistics on each of the columns here. And all the data frame is kind of a high-level wrapper on a big NumPy array in this case. It's got 2 components. So if I index out the values, I actually get a NumPy array. But it's also got something called an index. So you noticed perhaps this column of integers here that I didn't specify, but it endowed it with when I imported the data. It wasn't in the data itself, you'll notice, if you look up here. The index is fundamental because, and there are actually 2 of them. There's a row index and a column index. Okay? And so these are actually labels. So this one goes from 0 to 1632, and this one actually has string labels representing the column header names. It's more than just a set of labels. Pandas uses this for data alignment, which is really important when you get to larger data sets, really important when it comes to combining different data sets together. And to illustrate this, let's just let's make up some fake data. I just made up some fake data here. This is another, so there are 2 main data structures in Pandas. One is this data frame, this 2D tabular structure. The other is a series, which is basically just like an array with an index. Right? So I'm going to make up just, again, 10 random numbers. I'm going to give it an arbitrary index from 6 to 15 for no good reason. And then I'm going to join it. So I'm going to do almost like a database-like operation. So raw data, join more data. Let's see what happens without any other arguments or information. I get this. So it added it concatenated those columns together, but it did it in a smart way. It used the indices as an index, the row index of both data structures as an index to join them on. So you can see that for elements 6 through 15, we've got corresponding elements. Everything else has got NaN, which stands for not a number. It's what Pandas uses for missing data. So this is something else that Pandas and NumPy had to introduce because Python out of the box does not have missing values per se. So this is great, right? Because sometimes I'm dealing with hospital data with tens of thousands, hundreds of thousands of patients, and you want to join these things together. You can't go through row by row and make sure that patient information is corresponding with patient. You gotta ensure this programmatically. Yeah.
Can you create your own index and do it with more than one field? For instance, if you want to join data by date hospital.
Absolutely, you can do this by columns, by index. You can do it's extremely flexible. Wes McKinney, who's the creator of Pandas, has a really good and popular book on O'Reilly called Python for Data Analysis. I think it's not really about data analysis; it's about Pandas, but it's a really good book. It's hard to learn. It's great Pandas. You learn something new every time I use it. I learn something new, usually from Stack Overflow or something, or from his book. It's a really big pack. It's really only 2 data structures, but there's so much you can do with that in the context of data analysis that I'm always finding secrets. But that's the fundamental important thing about this. All right. So we're using these as keys. Now what you notice, and by the way, I didn't actually alter my original data by doing this. These are not, almost everything Pandas does is not in place. So it took raw data and joined more data and then returned it to me, but it does not change raw data in place. Raw data still is only just these 2 columns. It's a very important thing. So you got to assign that to another variable. You can override it and say in place equals true, but you usually don't want to do that. But anyway, I want to use a more interesting index than just an arbitrary set of integers. And if you look at the first column here, it says year. It's some sort of time thing here. And actually, it's the year and the month concatenated together, you'll notice. 1880 and the month 01. So you can actually assign whatever index you want. So I can take raw data and say set index and give it the column I want to use as the index. And I'm going to now assign this to a variable called temp anomaly. And now it looks like this. And the great thing about this is that you can use that index to pull out values of interest. So if I want to know what the temp anomaly was in June of 2015, I can index it out that way. You can actually slice, do what's called a slice as well. So take everything from 1940, 00, I don't know what 00, I guess that must be January. Who knows? Oh no, I see. Yeah, there is no, January is 01, but there was nothing to pull out there. All the way out to 1942, okay? And it sliced out those few years for me, which is great. You can also just do, integer-based, fall back and do integer-based slices. So this just says, show me the first 2. So if you don't put anything in here, it assumes it's 0. So it goes from 0 to 2, uninclusive. So it gives me the first 2 values. All right, let's have a look at this visually now. So let's visit plotting. We live in a good time now. Python has a very rich ecosystem of visualization libraries. This used not to be the case. The granddaddy of them all is Matplotlib, which I'm going to sort of use here indirectly. It's not very easy to use, and it does kind of stupid things. It's deliberately stupid. Like, it doesn't make any assumptions, doesn't try to make things pretty for you, because some people hate that, right? Don't make decisions for me. I'll tell you what to do. Just listen to me, right? Other people are, just make it pretty. I just want a publication quality, plot. I don't want to manually assign tick labels to things. Matplotlib doesn't do that for you. But it's a nice toolkit. So other higher level things are built on top of it. So things like Pandas has some plotting built into it, and a really nice package called Seaborn. Lots of other stuff. There's an implementation of ggplot for those of you that are R people. And then a lot of things that are based on JavaScript for doing things in the browser and having interactive plotting. Yes?
So does that mean that ggplot you have to incorporate R code in it? Or
No.
are you doing actually the code for it?
It's a complete Python implementation of ggplot. There's no
And
R
doing
required.
the same thing, you don't have to code in Java, you just do Python.
It's all Python, yeah. Yeah, it's written by the folks at YHAT. They're responsible for that. Bokeh is a really nice one. That's what, if I was starting today, I would be using more Bokeh. But anyway, this is great. The Jupyter Notebook's really nice because it allows plots to appear in line here. You do have to enable it. So I'm going to call these percent functions here are a Jupyter thing that are called magic functions that enable or disable capabilities within the notebook. This is just saying make all these plots, any plots I generate, put them in line here. Otherwise it will pop out a window, which you probably don't want in this environment. And then I'm going to import the Matplotlib plotting sublibrary.
Going back to the list of plotting libraries, which one would you say is the fastest? Let's say that I needed to make a scatter plot with 1 million points in it.
Bokeh.
Which Bokeh?
Yep, really good for that. Yes. Okay, and so there's Matplotlib, but I'm not going to use Matplotlib right away. I'm actually just going to call plot on my data frame. See what happens. So here we have a nice high-level plot, right? It made things look nice for me. Didn't plot all of the tick marks. That's what Matplotlib would have done. It just nice, evenly spaced ones. Even got a legend here, even though I don't need a legend because there's only one set of values. And I've got climate data, so this is great. And it looks great. You see, climate change is happening, and we can do things like zoom in. So let's look at just the first 25 values here, and you see something weird happening. So this isn't just a sequence of integers, right? As I told you before, right? It's year month, so it goes up to 12, and then it'll jump back to 1 again. That's what you're seeing here. But here it doesn't know this. So this is, sort of smart, but not that smart. It doesn't know that that's time data right now. So yeah, you look at the index and you can see that it jumps, right? So there are a couple ways of fixing this. One way is we can do some Python magic here. So here's one of these list comprehensions again. All right, so let's decipher what I've done here. Well, I'm looping over the index. For every element in the index, I'm doing something to it. And what I'm doing is I'm pulling out the first 4 elements. These are just string, actually these are integers right now. So I'm converting them to strings, pulling out the first 4, and then pulling out the remainder, and then I'm joining them with a dash. So it's going to say 1882-01 as a string, and then I'm going to use a Python function called toDateTime. It's going to turn them from strings into actual dates, because Pandas knows what to do with date objects. And so I get this datetime index. Look, goes all the way for, even adds a day, even adds the first day of the month for me. And that's great. An easier way to do it is to take advantage of functions already built into Pandas. It's got a function called dateRange. So I'm assuming here that there's no missing dates in all of this, perhaps a big assumption. So what I'm going to do is say start at 1880 January, and I want this many periods, so I'm going to take however many rows there are in the database, so shape, the first element of shape, and I want a monthly frequency. And so it's going to essentially generate the same thing for me. And so now I can add that index, set that as my index, and I've actually done a bunch of things here. And this is a common thing that you see when manipulating Pandas data sets called method chaining. So methods are functions that are attributes of an object, in this case, our big data frame. And it's got tons, like I said, there's a whole book full of methods and functions. And I'm going to do a couple other things here. I'm going to drop a column. I don't need the year column anymore. And I'm going to rename value to something, value of what? Well, it's a temperature anomaly, so I'm going to change it to anomaly. And I'm going to change these together, because remember, nothing's done in place, right? Every time it's returning me a data frame with whatever I've done to it. So it returns me a data frame with the index set to month range. Then I'm going to take it and drop the year. Then I'm going to take that and rename it. And then, finally, I'll assign it. So it avoids you having to make these intermediate variables that you may not have to use. And some people find it easier to read. Some people find it harder to read. I'm used to it, I guess. And again, you do have to do this indenting. Otherwise, it's impossible to read. But you can get really fast at doing that. So now I've got something really nice. And so now if I plot it, hooray, and if I zoom in, there we go. That's what I want, right? And you can do other things to tart it up, make it ready to go in a journal, right? So this is where, even though Pandas is this high-level thing that makes a lot of assumptions for you, you can actually go in and tool around with it using Matplotlib. So they're integrated, because one's based on the other, right? So it actually returns this set of axes. You may not have noticed, but back up here when I plotted something, it actually returned this set of axes. I just didn't do anything with it. Well, you can actually do things with it. I'm going to set the title. I'm going to change the font size of the title, set the Y label, set the X label. Okay, you can do lots of stuff. Yeah?
How does it handle large data? Like, so when you're taking it and you're transferring it from one data set to another, you had a 1 gigabyte data set, now you have 2 gigabytes of data, because you have one that's here and one that's here. So
right. Well, that's where that method chaining is really nice, because it doesn't make those, right? It just passes it to the next function, and then it ends up in the one that gets assigned. So yeah, I have been caught in a few situations. Look at my memory usage, and I'm up to 9 gigabytes because I've got, large data sets sitting there.
So it's all stored in memory. I think like Matplotlib does it that way, right?
Yeah, that's the important thing here. It's like somebody asked, well, why don't you use SQL for all this stuff? You can do that, but this is all in memory, right? This is all in memory in your Python session. And there are other packages. I'm not going to get a chance to talk about Dask, which is a fantastic new package that generalizes Pandas data frames to make them out of core. So you can work with tens of millions. There's a really good example using New York City taxicab data, where it's tens of millions of observations. It wouldn't fit in memory on a desktop system, and it works instantly because it's all out of core and parallel.
What's that called?
Dask, D-A-S-K. Okay, so time series. Like I said, this came from the financial world. So time series, it's all time series data that they deal with, and so I can do slices with dates formatted as strings, not even the same format as I gave it. So I want March 1990 through December 1991, and that's what I get. So it's pretty clever. If I want to resample, so I might want to smooth our data out. We saw lots of wiggles, climate, right? Today it's 20 degrees. 2 weeks ago it was 70 degrees. We want to smooth that out, right? We're not interested in weather. We're interested in climate. So resample to 2Q, again, financial stuff, quarters. So biannually, take the mean of it and plot it. Okay, that's where method chaining is really nice. Rolling window calculation, so rolling window of 12, so this is a moving average, basically an annual moving average. And do that, okay? So lots of stuff, lots of really good stuff in Pandas. And the nice thing is Pandas integrated with a lot of other third-party data analysis packages, like Scikit-learn, which I'm going to go to now. So now we've imported the data, cleaned it up, visualized it. Now we're going to do a little bit of data analysis with it. So Scikit-learn is the sort of premier machine learning package for Python. It's very robust, very well supported, meticulously maintained by its developers, and I use it a lot. And so I'm going to, and it does unsupervised and supervised learning. We're going to do some supervised learning here, some simple stuff. I'm just going to do some regression. So it's got a whole bunch of submodules. I'm going to use the one called linear model. I'm going to just do a regression line through this. Nice thing about Scikit-learn is its API is very clean and consistent. So everything, all of its methods, all of its objects, all of its analysis algorithms have a very consistent interface. It has an estimator interface for fitting models, a predictor interface for making predictions after you fit the model, transformer interface for transforming things, doing principal components analysis or factor analysis, that kind of stuff. And they're all like that. So you can really quickly iterate through different methods and try different things out without drastically reformatting your data, and everything kind of shows up as you would expect it to. So one of the things that it does is, so here, for example, I'm going to use a linear regression, right? And I'm going to set up my grid of values. So it's not going to use dates here, so I'm essentially I'm going back essentially to that integer index from before, and I'm going to call that my X grid. I'm going to initialize this linear regression object. I haven't fit it yet. Just this is what it looks like. And so I'm going to use the fit method. Right? So this is where you pass it data. So I'm going to pass it my grid. And one of the things that it expects, again, this consistent interface, it expects tabular data. So it has to be two-dimensional. So this reshape -1, 1 adds a kind of a dummy dimension to this because I've only got one column of data, of predictor data here at the time. And then the output can be essentially a single dimension. Okay, so I'm going to fit it. So I now have a fit model. The nice thing is it shows you what it's going to assume on your behalf. Linear regression is pretty simple, but for some of the other things, more complicated things like random forests and so on, there's lots of options. And one of the big mistakes people do when they use commercial statistics packages is they just use whatever the default values are for things and just run with the results. It's always good to know what's being done on your behalf. Like, oh, it's fitting an intercept on my behalf. You can multi-process this, so I could set n jobs equal to 4 and use all 4 cores to do this, and so on. So I fit the model. Now I can make predictions from that model, right? So this essentially will give me my regression line. So predict over that grid. So now I can plot these. Oh, and then all of the machine learning methods will have a score, some sort of score function that you can use to evaluate the model. This is an R-squared coefficient of determination in the case of linear regression. You can set what the score is, but the default here is R-squared. It's not very good, right? This is the amount of variability explained by the model, essentially. It's about 50%, which is not good for a regression model. And you can see that if you plot it, where to go? Okay, it's increasing. We knew that already. And this isn't a very good fit to the data, right? It ignores, it really underfits things up here. It doesn't account for a lot of what's going on here. So that's fine. Let's move to something then a little bit more sophisticated. I'm going to use, what I want to do, actually, is add a little bit of nonlinearity to this model without going too crazy yet. What I'm going to do is it sort of looks like there's kind of almost a homogeneous thing going on in here somewhere, and then we sort of get this hockey stick thing, right? It starts increasing at a faster rate after the 70s. What do you know? I want to account for that. So what I'm going to do is I'm going to fit something called a piecewise linear model. I'm going to fit a linear piece here and a linear piece there. And I don't know where there is. I don't quite know where the switch should be. So I'm going to estimate that too. Okay. So I'm going to adopt a Bayesian analysis approach, where anything you don't know, you can just add it to the model as a variable and have the model fit it. So it's going to figure out automatically where the good change point's going to be, or it's going to try to anyway. Bayesian statistics is an alternative statistical paradigm, and it's based on probability modeling. What it does is you endow, as a user, you endow things you don't know, things you want to estimate with probability distributions that describe what you know about it before you've done your experiment or your study. So often it's nothing. So you make some big, wide probability distribution. And then you add data to it, and you get what's called a posterior distribution that tells you what you know about your data after observing, or about your model parameters after observing the data. And it's called Bayesian statistics because it uses Bayes' formula to do this. So theta here are my parameters, all the parameters of a model, so it's like a vector. That's the prior probability. Then I add data, so y is my data. So the probability of my data given what I thought about it, the system before I did my experiment. And this transforms it to, basically flips this conditioning around. The probability of theta given y. This is what I want to know. What do I know about theta after observing y? Okay. So this posterior distribution is the goal of inference here. So I'm going to calculate the posterior distribution of this piecewise linear model. I'm going to use this package PyMC that I started a long time ago when I was a postdoc. People have added lots of. The reason it's great today is not because of me. It's because of lots of really smart mostly grad students and stuff, right? Who have lots of time to I don't have time to do all this anymore. And so really good stuff. It fits almost any model you can write down in Bayesian, in a Bayesian context. Does all sorts of summarization of output, tables and plots, tells you whether your model fits or is converged or not, and so on. The current version is based on a package called Theano. Theano is an expression evaluation package. Essentially, it's if you've used, you might have heard of TensorFlow before by Google. Theano's sort of another implementation of that. It's much older than TensorFlow. It's from the Lisa lab at the University of Montreal. And Yoshio Bengio is one of the big deep. So it's a deep learning library. People use it for doing deep neural nets and stuff. We're using it here to implement Bayesian modeling. So I'm going to import PyMC3 here. And this is the model I'm going to implement. So first thing you got to do if you're Bayesian is endow all of your unknowns with priors. So my intercept, I'm going to give it a normal mean zero with a standard deviation of 100. Like really wide. We don't know anything about this. And then two means, right? Slopes. An early slope and a late slope. And I'm going to say we also know nothing essentially about that. An observation error. There's lots of observation error in that. And then here's the cool thing. This is my switch point that I don't know. I'm going to assign it a discrete uniform between 0 and 1632 because that's how many months there are in my data set. So it could be anywhere in there. And then I can assign some transform parameters. So if you're in the early phase, so if your time is less than tau here, then it's the early linear regression. Otherwise, it's the late linear regression. And then we add the data. So the likelihood is how the data influences the values of the priors. And here I'm just going to say that it's normally distributed. Not an unreasonable thing in this case. With whichever mean corresponds to t. Sorry, that should have a yt there. And there's the observation error. Okay? And the nice thing about PyMC is that it essentially takes these statements, translates them to code, and you're done. So I instantiate this model. This with statement is a Python, it's called a context manager. So essentially, it provides this model as context, and when I'm creating all of these variables, it's automatically adding them to the model without me having to add them manually. So I'm going to create my data from my data frame above, and then here we go. Normal intercept prior, normal prior on the early slope, normal prior on the late slope, uniform prior on sigma. The cool thing now about Python 3 is that it's Unicode, so you can use actual Greek letters here instead of writing out sigma. Tau, same thing. Early and late phase means, that's those other two lines in my code here. And then two likelihoods, one for early, one for late. I could have concatenated them to do it in one line, but there's no need to be fancy. Okay, and so that instantiates the model. Then I run sample on that. And so the problem with Bayesian inference is that it's hard to do. It's impossible to solve analytically. To get this answer analytically, it involves multidimensional integration, which is hard after like two variables. For me, one variable. For most people, two variables. And so what you have to do instead is do a numerical approximation. And so this uses a Monte Carlo-based approach called Markov chain Monte Carlo. And so what it's doing is it's sampling from the posterior distribution. And so this is what's going on here. It's generating kind of 10,000 samples. And how fast or slow this goes usually depends on the size of the data. Larger data sets take longer because it's got to evaluate this likelihood for every data point. So we've got 1,600 size data set here, and it's pulling that out for me. It makes a lot of decisions for you, okay, which you can override. It says assign nuts to intercept. What the heck is that? Nuts. And then Metropolis to the other one. Nuts is an algorithm called the no U-turn sampler. It's a particular flavor of Markov chain Monte Carlo that's very efficient. And Metropolis is a different one. So it's choosing appropriate samplers to use for each of the variables in the data set here. I probably didn't even need to do 10,000 of these because it converges pretty quickly. And then it'll monitor this for you. And so what you'll get at the end is this multi-dimensional vector called a trace. So it's all of the samples that you get. Once you get all those samples, you can get a distribution, approximated distribution for each of the parameters. So you can pull out probability intervals. You can say, how many of these samples are greater than 0, or is this distribution larger than that distribution, and so on. What else?
Should have run it on the cluster.
I should have run it on the cluster. Yeah, and that's the other thing, is this is very easily parallelized. I could have gone n jobs equals 4 and divided it by 4, and I'd be done by now.
Would you use Patsy or?
Yeah, you can use Patsy. So there's another, if you're just doing linear regression models, simple ones, we've got a submodule called GLM, so pymc.glm, and you can say y tilde x, or y tilde x squared, or whatever. Use Patsy. Yeah, Patsy is just those of you that use R, you're used to seeing equations expressed as y tilde x for a regression of x on y, and you run linear models on that. You can do a similar thing with a library called Patsy. We're almost done here. My computer's faster. I've got a newer PowerBook, so mine was done.
Or that encoder I have running for the stream.
We got stuff going in the background here? All right. Okay, it's done. So now we get these things called a trace plot, right? So these are all the variables. This is the trace, right? This is the actual. And these all look good. This is what you want, sort of a homogeneous time series of values here. And I can extract these guys, generate predictions, and plot it. And now we see our little outlook. That's kind of cool. But this still isn't super satisfying, right? Because it's still ignoring, it's not a great fit. Unless you really just want some underlying, maybe you do just want an underlying linear trend, but just know that this is not a linear process. Right? We're using a linear model to model something that's not linear. Can we make a nonlinear model? Yes, we can. So what you can do is there's another type of Bayesian modeling called Gaussian processes. And Gaussian is just another word for the normal distribution. And what you can do is model this time series as an infinite collection of, well, not infinite in this case, a set of multivariate normals. You just say that every point is multivariate normal, right? So you might have done splines before where you set these knots, and you can do different things to join lines between the knots. Well, here you're essentially having a knot at every value, right? So it's sort of a generalized spline. Gaussian process is just, you can think of it as a distribution over functions. So it doesn't try to model slopes and intercepts. It tries to model forms of functions that can be weird and wacky. And the way that it does it is using a covariance function. And the covariance function describes how different one point is from one next to it, or one further away from it. And generally these things, you're more independent of, 2 points are less dependent of one another the farther apart they are. And so you can then model all of this autocorrelative stuff that's going on here. And so what you have to do is pick one or more covariance functions, pass it into the Gaussian process, and then let it fit this nonlinear, arbitrary nonlinear function. So for example, a common one is a Matern covariance. That is a 3-parameter covariance function that allows for, depending on how you parameterize it, very jagged ridges in the covariance function. You can stretch things out to smooth them or squeeze them together to make them less smooth, those sorts of things here. And the nice thing about Gaussian processes is that the covariance functions are additive. So you can model different components of a nonlinear process. So in this case, I might have, like a constant function, like a scale, something that scales it. If I do think there's this underlying linear trend, because there might be if it's climate change, a dot product kernel. It's just some linear function. Here's this Matern thing that we talked about just now. This is going to model most of the nonlinear stuff. And then what's called a white kernel, which is white noise. So this is essentially observation error, just random fluctuations that's not really described by anything. So I've got this compound kernel here, and all I have to do is, oops, I didn't import. Didn't run all of these things. Here we go. I'm going to use Scikit-learn for this. And I'm going to build this kernel simply by adding these instances together. Instantiate a Gaussian process regressor with that kernel. And then just as I remember, same interface. X and Y, and then call fit. And Fit will take a little longer this time because it's a bigger model, and it's essentially it's maximizing the marginal likelihood of the model. So it takes not quite as long. So it runs an optimizer underneath this. There's another package that I didn't talk about called SciPy, which is a very rich library of scientific functions, including a whole set of optimizers. So this is using the BFGS algorithm to optimize the hyperparameters of the ones that we didn't pass it explicitly. When things are fit, what happens in Scikit-learn is it endows the resulting, in this case, Gaussian process object with a bunch of attributes. So you can see what your kernel ended up looking like. Right? That's what ends up getting fit. And then you can make predictions about things. So, for example, we might also want to know what's going to happen to the climate in the future. So beyond the time series. And you wouldn't have wanted to do that with just the, hockey. It's not just going to go up forever, right? You saw that there's quite a lot of nonlinear fluctuation. What if it comes back down again? So what I'm going to do is give it a grid with additional variables. So I'm taking my x and concatenating an additional 100 years onto the end of it. Okay. And now I'm going to use that Gaussian process to predict. So I'm going to get predictions. I'm going to get a line. And I'm going to get, for each point, I'm also going to get standard deviations, and I'll call sigma here. So I'm going to get not only an estimate, but also, importantly, an estimate of uncertainty. That's the key here. That often gets missed in machine learning applications. How certain are you about your answer? So now I've got something that looks a lot more reasonable, right? This sort of looks like what's actually happening underneath, sort of the data generating thing. I don't know what happened to my credible interval. It kind of collapsed on me here. That's weird. Didn't do this on my machine. Anyway, you're also getting 100 years prediction. So actually it's predicting a flattening out here. Just again, it's only based, this assumes that what's going to happen in the future is the same as what's going to happen in the past, and that's not something you want to assume. But people do want to make predictions, and this seems to be a sound way of doing it. Okay, that was a lot for an hour. This is the original. This is where I stole the example from, if you want to look at that as well. And like I said, there's lots more resources for all this stuff. O'Reilly books, websites. There's a whole, most of these packages, particularly PyMC and Scikit-learn, you'll find a bunch of these notebooks bundled with the packages that demonstrate how to do, Bayesian regression or principal components analysis or whatever. So you can go hunt for those if you want to get runnable examples on your machine. Okay.
Any questions?
So the book you suggested was that Python for data analysis. That's what came in.
Yeah, it's got one of those animals on the front, red. Yep.
Right.
Yeah.
All right. Let's thank Chris.
Thanks.